Hello, everybody. Let us start our discussion today. We have been following a few experiments and trying to see the development of a new theory called quantum mechanics. And in the few experiments, we have learned a few things. And today, before we start the fresh discussion today, let us go through the timeline of things happening in 1800s and beginning of 1900s. So first, we'll go back to 1862. This is when Maxwell came up with the compilation of electrodynamics. This essentially said that light or radiation is electromagnetic wave. So let me write EM for short form for electromagnetic waves. 1886, as we have heard, Hertz proved existence of EM wave. He also observed the photoelectric effect. In 1897, let me put it in a different color because we are talking about radiation here. 1897 is a different thing. It's a discovery of electron. You may ask, why do I put in electron here? It will come to our understanding. We will know why I am putting electron here shortly. So this was J.J. Thomson. Back to radiation, 1900, explaining black body radiation, Max Planck So he had to assume that the energy exchange between the atomic oscillators and the radiation inside the black body cavity was happening in discrete steps of h times nu. 1905 came Einstein. With his light quanta hypothesis. Now here Einstein said that the radiation does not travel in like continuous waves, but it seems that it is easy to explain photoelectric effect. Actually, he explained black body radiation and other phenomena, I think 7 phenomena. So total 8 or 9 phenomena were not explained at that time. Einstein explained all of them using the light quanta hypothesis. He even gave a better explanation of black body radiation in the same paper. So he said that the light or the radiation travels and it gets exchanged in packets of energy, and these packets are discretely distributed in space. So if I go to a part of the space at a given time, then I will get the packet, and the packet may move out of that part to some other part in space in a later time. So this is starting to behave. So here we should say that radiation seem to have localized properties. (1913), so I still keep it in white because, so this is Bohr atomic model, Niels Bohr atomic model. There he explains the spectral lines that one sees from hydrogen and other elements, why there is spectra emitted only at a given frequency but not at all frequencies. So that is what the Bohr atomic model could explain. He also explained the value of the Rydberg constant, why the value is whatever the value is. And you have learned these things in your plus 2, so I'll not go through them again. So here, let me remind you that one hypothesis was that one hypothesis was that the difference in the atomic level was integral multiple of was h times the nu. So one hypothesis was that the difference in the electron level is h times nu, where nu is the frequency of the light emitted when electron gets transited from the upper level to the lower level. And this is in line with Planck's hypothesis, where Planck also is assuming that these atomic oscillators emits in discrete energies. So Bohr atomic levels are discrete. The other hypothesis was that the angular momentum is given by n times h cross, where h cross is h by 2 pi. So it's essentially another form of Planck's constant. H is Planck's constant, obviously. So this was Bohr's atomic hypothesis in 1913. So it's one way it is discretizing the energy levels in the atomic oscillators or hydrogen atoms, whatever you say, and that's how it is is explaining why there are radiation of only certain frequencies which comes out of these atoms. It also is telling you that what is the angular momentum. The angular momentum is also quantized. It only comes in integral multiple of h cross. So this is 1913. Let me come to 1924 now. I'm sorry. So I forgot the Compton scattering. So which we discussed last time is happened in 1923. Compton scattering, where Compton used the light quantum hypothesis to show to explain Compton scattering, which we discussed last time. I will come back to a very important observation in Compton scattering shortly. So that happened in 1923. Now come back to blue again, because now in 1924, what we are talking about is not radiation but matter, and this is done by Louis de Broglie. Louis de Broglie in 1924, he gave a very, very strong claim. He said there exist matter waves, and this is what we will discuss in more detail today. But let me just keep it here. And in 1926, Davison and Garmer. So let me write D and V here because this is again something that we'll discuss in detail. Davison and, I'm sorry, not V, Garmer. They saw electron waves, and again it seems very unsettling, but we will settle it shortly. The same was seen by G.P. Thomson in 1927. And since G.P. Thomson is son of J.J. Thomson, J.J. Thomson here observed the electrons first as particles. And G.P. Thomson observed electron waves. So you see, in 30 years, things has changed. Father and son duo is discovering that electron is both particle and wave. Now there is one interesting thing that happened out of discussion between Niels Bohr and Einstein in 1924. Niels Bohr suggested, this is actually before the electron waves, suggested nature have dual properties. Particles and waves. Which essentially means, so what he suggested is that I cannot say whether electron is a particle or electron is a wave until I tell you how I am trying to look at the electron. Electron may appear as waves in certain experiments and may appear as particles in certain experiments. So to understand that, before we dig into the blue parts of the story here, let us discuss a little bit about what is the actual difference between particles and waves. So particles versus waves. Okay, and really there is no boundary, so I'm not drawing a boundary here. We said that we are discussing today dual properties of nature. So what is a particle? So particle is localized. It has a definite, so localized means have definite position. At a given time. So it's both localized in both position and time. Okay, so that is what we mean by a particle. Usually it is considered as a point-like object which has a definite position at every time. And how much it changes its position in a given unit of time, we call it velocity, etc. Waves is opposite, it's non-localized. It can, I will not say every time, but it can exist everywhere. In position and time. So like when I write a wave, say we were denoting wave by phi, and let us consider one position coordinate only. So this we are writing at, say, some amplitude phi 0 sine kx minus omega t. Okay, so now you see that this sine curve, if I plot it at a given time, so t equals to t0, say, if I want to plot this, the sine curve will look something like this as a function of x. But it looks like this for all function of x. Sorry, all values of x. So there is a value of the sine function for all values of x. I can do the same thing for, instead of t equals to 0, I can choose any position. I say let's choose x equals to 0, easiest one. So again, if I plot it against time, you see it's sine of minus omega t, so it will probably look like this against time. So you see this is not localized, it's non-localized, so it exists everywhere in the space and time, or it can exist everywhere in the space and time. Here we have talked about one particular example which exists everywhere in space and time. We can have other examples also, which maybe it exists somewhere in space but at all time, or somewhere in time and all space, and it can have more existence at some point, less existence at other points, etc. So those examples we will see later, but at least it can exist everywhere in position and time. So that is a wave. That's a basic difference between the concept of wave and the concept of particle. What is the observational difference? The observational difference is the waves show interference. Interference, diffraction, this type of things. Diffraction is also an interference, but nevertheless, the waves show this. For example, we discussed that if I have two layers from which the wave is getting reflected off, and they has a thickness A, so the wave is coming this way and getting reflected off this way. If it is coming with a grazing angle, say, I'm already calling psi something, so this is phi, then the condition for maximum intensity is 2a sine phi equals n times lambda, where lambda is the wavelength of the wave. So this is a phenomena of interference which happens only in the wave. Particles, however, cannot or does not show, particles do not show interference. Interference, diffraction are only wave properties. So by this we can distinguish. So you can, if we see that something is showing interference or diffraction, we will be sure that it's a wave, it's not a particle. As a matter of fact, there is one more thing which we have already discussed, that as a consequence that these are localized in space and time, the energy exchange between particles is almost instantaneous. Instantaneous is those not a very good word, but still the energy exchange between the particle happens in very small time. For waves, it takes time. And that is easily understood because the wave is distributed over both space and time. The energy of the wave is also distributed over space and time. So you need so if I am considering receiving the energy of the wave at a given fixed point in space, say at x equals to 0, so I will require enough amount of wave to reach that point. before a bulk some energy exchanges happen. So it takes more time. This we also saw while discussing the photoelectric effect. Okay, so now these were in the back of our, this we should keep in our back of our mind, what is the difference between the waves and the particle. Now let us just discuss a little bit back about Compton scattering. We have already seen Compton scattering and we have not noticed something interesting happening here. Remember that I will just draw a block diagram of the apparatus here. So I have an X-ray source here. Which falls into the scatterer, which is the graphite. So here I have scattering happening, which involve inelastic scattering. And Compton concluded this must be happening by light quanta. So X-ray light quanta must be scattering this. Must be getting scattered of the electrons, free electrons in this scatterer. And then so this is X-ray falling into it, and then it goes to some direction. And then you have a spectrometer here. X-ray spectrometer. Interestingly enough, the X-ray spectrometer, remember that we have assumed that X-rays as light quanta when it is getting scattered. But remember, the X-ray spectrometer works on this principle. So there is some crystal sitting over there, calcite in case of Compton, and we are looking at the interference phenomena happening through this crystal. So works on interference. So you see, we are looking at one experiment where in this case, you are saying that I need to consider X-ray as light quanta like particles, and here I am saying that I need to consider X-ray as waves because I am looking at interference of X-rays. Compton scattering already is showing dual nature of radiation in one experiment. Okay, to be more precise, it's two different parts of the same experiment, but at least within the setup, you see the dual nature of the radiation. I'm avoiding saying light because when I say light, we mean a very particular part of the electromagnetic radiation which falls in certain wavelength or frequency range. But if you wish, you can also say light. So the radiation, at this point, we already know has dual nature. In certain cases, it behaves like light quanta or particles. In certain cases, it behaves like waves. Now let me tell you a very small amount of story, and let tell you how our understanding of nature was changed in 1924. So 1924 came a very nice thesis with the hypothesis of Louis de Broglie. Maurice de Bruy, who is the brother of Louis de Broglie, was a physicist, And Louis de Broglie was doing rather arts, he was doing history. And Louis de Broglie comes to visit Maurice de Broglie, and Maurice de Broglie was involved in this very, very peculiar thing that recently people have seen, this dual nature of radiation. The radiation, which is supposed to be a wave, also has particle-like properties. Certain experiment could not be explained if you don't see particle-like property, if you don't assume particle-like properties of radiation. So, in coming to the elder brother, Louis de Broglie said that, okay, I will investigate about these properties, these dual properties. And in 1924, he wrote a thesis along with many other things. I'll keep a link of this also uh, in the Google Classroom link, because this is something that one should read at some point in life. Maybe not during the course, but later, if you have downloaded the Bro's thesis, you may download and see. Now, the actual assumption de Broglie did was a little different than what I'm going to tell you. That is because the actual assumptions and then what I'm going to tell you is a corollary of that assumption. But this is what is celebrated as the de Broglie hypothesis nowadays. So, because of that, I will just tell you this as the de Broglie hypothesis. So, what he said is a very bold statement. Till now, what people have seen is that radiation has dual nature, but de Broglie says this: everything in nature, so light, or should I say radiation, so this is electromagnetic radiation. If you wish, I write electron here, which is cathode radiation, if you know it already. So everything in nature have an associated with wave with it. Of wavelength. So a wave always have a wavelength lambda, say, and a frequency nu. When lambda is given by, so let me write this as lambda d, so it is de Broglie wave lambda is h by p, and omega is given by E by h cross. Okay. It is obvious, but still let me write down. P is the momentum of the wave, or momentum of the particle. Let me write momentum here itself. So if I am considering a particle, to calculate the corresponding de Broglie wavelength, I have to use the momentum of the particle, and E is the energy. Okay, a quick check. So remember, so let me tell you why it is so bold. Electron wave was not seen till now. Only it was observed that the radiation has particle-like properties. And de Broglie is hypothesizing that this dual nature that is seen for radiation should be seen for everything else also. At that time, electron was everything else was, for elementary particle was electron. So for electron also you should see this. Now for photon, this works out very well. For photons, for radiation, We know that lambda of the radiation times nu is the speed of the radiation, and nu is omega by 2 pi, so which is the speed of the radiation. This we know for radiation. Radiation is light, and with special relativity we saw for light E equals P times C, momentum times C. So if I say now using the Broglie hypothesis that E is omega h cross, here I am using the Bruy, and P is h by lambda, so then I get this expression. So this is omega into h by 2 pi, and I can bring lambda this side, equals hc. So from this you see that, get back that. So this is the left hand side is the particle side, the right hand side is the wave side. For radiation, we know for wave lambda is lambda times nu equals to c, or lambda times omega by 2 pi equals to c. And for light, we know that E equals to P into C from special relativity. So this is STR, gives us this. And then if I use de Broglie hypothesis there, I get back that same relation with the wave. Right. One thing where de Broglie applied his hypothesis was Bohr's theory of atom. Remember that this is 1913 where Bohr's theory came up, and he had this assumption that the angular momentum is nh cross, n times h cross, integral multiple of h cross. De Broglie hypothesis in 1924, well after Bohr's theory. So what de Broglie said is that for Bohr orbit, n equals 1 Bohr orbit. So for Bohr orbit, the angular momentum is nh cross. For n equals to 1, it is just h cross, which is h by 2 pi. Now, what is the angular momentum? The angular momentum is the moment of the linear momentum. Linear momentum is, say, p for the first orbit, and because it's a circular orbit in case of Bohr, it is, say, the radius of the first Bohr orbit times p. So this is equals h by 2 pi. Now if I replace the momentum using the Broglie hypothesis, the Bruy hypothesis, then lambda of the first Bohr orbit will be h by p, or p will be h by lambda. So you get Rb by lambda b equals 1 by 2 pi. I forgot to put the h here. Okay, the h gets cancelled out, sorry. So you see that the first Bohr orbit is 2 pi times the de Broglie wave, essentially, wavelength. And actually we are reverse engineering it here, but actually Bohr's hypothesis was arrived by de Broglie from de Broglie's hypothesis. So de Broglie started from here and could show that L will be n times h cross. Now let us ask the question that what will be the wavelength of the de Broglie wave? Okay, so let's take few examples, and we are taking non-relativistic examples here. You can consider relativistic examples as homework. So non-relativistic examples. De Broglie wavelength, the Bruy wavelength. Remember, we are talking about a wave with a wavelength and the frequency. We have not talked at all about what is the wave of. Like sound wave is pressure waves, electromagnetic wave is waves of electric fields and magnetic fields. We don't know yet, and de Broglie also did not talk about what is the wave of. That we'll come back to later in the course. So the momentum of such a wave is related to the energy of the wave in the following way. So P square E is kinetic energy is given by P square by 2m. So this implies that P is root over of 2m times the kinetic energy. So you can say directly that the de Broglie wavelength of a wave which has kinetic energy Ek is h by root 2m Ek. Okay, so let's consider examples. If we put in the kinetic energy, we should be able to figure out what is lambda b. So let's consider examples of, so example, and I guess in my generation everybody knew of Shoaib Akhtar. I guess in your generation also you know of Shoaib Akhtar, who used to be one of the fastest, probably the fastest bowler in the world cricket. So say Shoaib Akhtar is bowling towards say Sachin Tendulkar, and the velocity of his ball is 160 mile per hour, say 200 kilometer per hour. Shoaib Akhtar never bowled so fast, but let's assume this is the number. And mass of a cricket ball is around 500 gram, which is 0.5 kg. So I can now calculate what is Ek. So Ek is half mv square, so 0.5. The Ek I can also calculate by p square by 2m directly, or I don't, in this particular case, I don't even need Ek. I can directly calculate the momentum, but let's calculate E square, Ek once. So this is this times 200 kilometer per hour, so which is 200 into, it's a half which I'll forget, so let me write down 200 kilometer per hour. If I convert to second, it will be this many per second, and let us write meter per second. So this is multiplied by so many things and then square. Okay, so this is kg meters square second minus 2. Calculate this. So I request you to calculate this. The reason I calculate Ek is that de Broglie is not only talking about the wavelength, he is also talking about the corresponding frequency. So I can calculate the frequency now. Omega p, which is the omega b, which is the frequency, angular frequency of the de Broglie wave, will be simply Ek by h cross, and we are assuming there is no potential energy here involved here. If you calculate it, it will come out to be of the order of 10 to the 46 Hz. extremely fast. How fast is 10 to the 46 hertz? Well, as we know, our clocks oscillate once per second. That's why you get 1 second for each oscillation of the clock. If you have a fast computer, your clock of the computer oscillates 5 into 10 to the 9 times a second, say 5 gigahertz computer, which is also very rare. If you consider the oscillation of electromagnetic waves, that is 10 to the 14 hertz, which is 10 to the 14 to 10 to the 15 times a second. This will shadow everything out of the window. This is 10 to the 46. It's even like 10 to the 30, 31 times faster than the electromagnetic wave. What would lambda be? Lambda b is given by h by p. P is m times v, as we are considering non-relativistic case. And this, if you calculate, will come out to be of the order of 10 to the minus 35 meter. Please check if the de Broglie wavelength is of this order. I can be wrong here, so let me put a exclamatory marks. But please check by yourself. This is a simple calculation. You can put in the numbers in your calculator and check. This is again very small, much smaller than the atomic dimension. The dimension of the nucleus inside the atom also is like 10 to the minus 14 meter only. This is extremely small. So what happens if I have these things as small? Well, when you are looking at the screen, let us ask the question, a completely different question. Let us ask the question, what is happening as you are looking at the screen? You see that things are moving here, right? How do you see that the things are moving? How is that movement produced in the screen? Well, the screen, as it may feel like a constant thing to you right now, is not quite constant. It's being scanned by, it's made up of many pixels, and the pixels are changing their intensities. In this particular screen you are looking at, depends on your device, but it may be 30 to 60 times a second it is changing intensity. But our eye is capable of only seeing, say, 10 to the 20, only seeing 20 times a second, things changing at 20 times a second. Anything faster, our eye will not be able to make up, will not be able to find. To observe anything of frequency omega b, we need some measurement device that works as fast as omega b. Actually, it has to be twice faster. But let us not go into that detail. But it has to be all of the order of omega b. So I need something which changes 10 to the 46 times a second. I don't have anything like that. So I'll never be able to see the oscillation with frequency. So if I want to plot or want to measure the oscillations of the de Broglie wave with time at a given point in space for the ball thrown by Shoaib Akhtar, I'll never be able to see it because this. Similarly for lambda b. So as we have seen, for X-ray, we needed a spectrometer which had the spacing between those layers of the order of angstrom, because X-ray wavelength is of the order of angstrom. So to see such a wave of a wavelength lambda b equals 10 to the minus 35 meter, I need some spacing. If I want to make the spectrometer just like the X-ray spectrometer with a crystal, I need spacing which has 10 to the minus 25 angstrom is the spacing. Because remember, 10 to the minus 10 angstrom is 1 meter. This is 10 to the minus 35. I need 10 to the minus 25 angstrom as the crystal spacing. Well, that we don't know of anything which can have such small spacing. So this type of wave, which is created by regular objects, if they are there, we'll never be able to see them. That is our first example. On the other hand, let's see what happens if we consider another example, and this time we are considering electrons of energy 56 electron volt. And why this particular number will come back to later. But what is an electron of energy 56 electron volt? Can we produce such an electron? Well, that is easy. What all you have to do is you need to have two metal plates between which you maintain 56 volt and you put an electron here. The electron will get attracted by the positive force, positive plate, and it will have, so if it starts from 0 volt energy, then as it is going down from the negative plate, it will have 56 electron volt of energy. If you calculate the de Broglie wavelength for this, remember how to calculate this is H by P, and P in this case will be EK M E, and I need a 2 somewhere, so multiply by 2. So this is exactly the same formula that I have written here, but now for the electron of energy EK, and the energy 56 electron volt, we can, very well how to translate it to joule. I have to multiply E times V. So I put 56 for V. This is 6.6 into 10 to the minus 34 Planck's constant. Electron mass is 9 into 10 to the minus 31 kg. Electron charge is 1.6 into 10 to the minus 19 coulomb. Once you put in all this, you will get a lambda B. This is for 56 electron volt electron. This will come out to be 1.67 angstrom. Wow. So this is just something that even those calcite crystals will be able to see. So imagine that I have, say, some type of crystals where the atomic spacings are 1.67 angstrom. Then that is supposed to see this electron as electrons, many electrons falling into it with this wavelength or with this amount of kinetic energy, 56 electron volt. It will see that as waves and it will produce diffraction pattern. This de Broglie wavelength of the electron is quite comparable to the atomic spacing. So we should be able to see these de Broglie waves using atomic spectrometers or crystal spectrometers. That is what we will discover in the next day, where we will discuss the experiment by Davisson and Gummer, which was done in 1926. They initially wanted to do a little bit different things, and they did not know of de Broglie hypothesis to start with. De Broglie, Niels Bohr, and Einstein, all others were in Europe, where Davisson and Gummer was working in United States of America. And at that time, there was no internet in 1926, so they did not know what is happening to their experiment. But then when they came to know about the Broglie hypothesis, they could explain the outcome of their experiment. So today we have learned that it is not only seen that the light has both wave-like and particle-like properties. It's not only that in Compton scattering we saw both of these properties in play for scattering and measurement of the spectra of the X-rays. But in 1924, de Broglie came with a hypothesis which said that it's not radiation but everything has these dual properties. Everything that we call matter, there is a wave associated with it, which eventually was called matter waves, which has a wavelength given by h by the momentum of the matter, and an angular frequency given by E by h cross, where E is the kinetic energy of the matter. So this is the de Broglie hypothesis we discussed. We saw how it could be used to explain Bohr's hypothesis of angular momentum quantization. And we saw in two examples how big or how fast the de Broglie wave length or the de Broglie frequency will be. In case of ordinary objects like Shoaib Akhtar's cricket ball, such wave cannot be seen because it oscillates too fast and the wavelength is too small. But case of electrons with 56 electron volt of energy, the wavelength is 1 angstrom, quite measurable. So I request you to calculate the corresponding frequency of the de Broglie wave as a homework. You will see it will come out to be almost of the order of optical frequencies, if not the ultraviolet wavelength frequencies. You can guess what the frequency will be just looking at the wavelength here. So I'll stop here. In the next lecture, we'll start from here and see how divisional gamma, and also mention about how G.P. Thomson proved that electron has wave-like properties. Thank you for today.